Alright, I thought I'd make a derivation video that is separate from some of our suggested problems, just in case you want to see the derivation of Ampere's law on different geometries of current carrying wires. So first up we have a long straight wire. Okay, and we're applying Ampere's law, where we have a closed line integral, where the line piece comes in right here, our green differential path vector. It's different from Gauss's law, which was a closed surface integral. Here we are taking a path at some starting point and going around in a closed loop. In this case, we're going around the wire in a circle. The radius of that circle, which is how far we are from the center of the wire, tells us the strength of the magnetic field at that point. That distance from the center of the wire can be inside our wire, it could be outside of our wire. Just ensure that if we're inside the wire, the enclosed current of this little path we're taking around the center point of the wire only includes the current flowing through that circular cross-section. Okay? Anything outside of it does not count. Alright, so let's take a look at this. First and foremost, we want to choose a path that makes this integral as simple as possible. So, if we have a long straight wire, the simplest path for us to take that keeps the strength of the magnetic field constant is to go in a circle around the wire. If we chose to take a square path, then guess what? At the corner of the square, the magnetic field is going to be different from somewhere in between our vertexes or corners. That doesn't help us. That makes this an extremely complicated integral. But when we choose a circle, the strength of the magnetic field at anywhere on that circle is constant. And if we have a constant inside the integrand, what can we do with it? That's right, we can pull it out. Okay, so let's make that our first step. We still have, wrong color. We still have our closed loop integral, but the strength of our magnetic field is constant. It's not dependent on where we are on this circular path. Okay, that's important. So now we still have our differential path vector. And the reason I went to magnitude is because I'm converting this dot product to magnitudes and angle. It's still equal to the permeability of free space times the current enclosed by our loop. In this case, our loop contains the entire wire. So the current enclosed by our loop is the current in the wire. So, what is the angle between our vectors? Well, so we look at our diagram. Here our differential displacement vector on the right hand side. We have our differential path vector is into the page or into the screen, and our magnetic field is into the screen. We know the direction of the magnetic field based off our right hand rule. If you want to see that in action, look at the video for lesson 37. Alright, so if they are both pointing in the same direction, then the angle between the vectors is 0 degrees. And the cosine of 0 degrees is 1. Alright, so now we have the magnitude of the magnetic field times the closed loop integral, and that's equal to what it was before. Okay, now the closed loop integral is really just adding up all of these teeny little path elements. And if you add them all up, then you get a circle. And what is the total distance around a circle? That's right, it's the circumference. Now I'm getting all these dots because my hand keeps touching the screen. I apologize. So we have the strength of the magnetic field times the circumference. And what's the equation for a circumference of a circle? It's just 2 pi times the radius, or 2 pi times the diameter. And if we're solving for the strength of the magnetic field, then we isolate that specific variable. And that's what we get, and that is what's on our PRC. Alright, next up is a circular wire, or a circular arc. Alright, so here we have our circular arc. Now granted, this is just a portion of a current carrying wire, which may be straight or turning different directions, but here we're specifically looking at the circular arc portion of that wire. Alright, notice that using the right-hand rule, our magnetic field is out of the page on the left-hand side, and on the right-hand side it's into the page. In this case, for this geometry, we're actually going to start with the law of Biot and Savart. Okay, instead of using Ampere's law, which is integral form, we're going to use Biot-Savart, which is covering the same stuff, but it's in differential form. So here's the law of Biot and Savart. The way this works is that we are looking at the differential amount of magnetic field contributing at our center of the arc due to tiny little pieces of wire right here. Alright, so the current in the wire right there in this tiny little path segment ds at a distance r away contributes a differential amount of magnetic field. And as we continue to add up the chunks of wire, they all contribute to the magnetic field at this point. And that's dependent on how much of a circular arc we have. Is it a full circle? Is it just a tiny sliver of the circle? Well, that's where this angle phi comes into play. So we can see that because we have a circular arc, our radial unit vector, r hat, is always going to be 90 degrees from our differential path vector ds. So we can simplify our cross product right here. So now that I have simplified the cross product, we now have to work in magnitudes. So we have the magnitude of the differential magnetic field, and we have the magnitude of our differential path element times the magnitude of our unit vector, and the magnitude of any unit vector is just 1. And that is multiplied times the sine of the angle between our vectors. And as I said before, the angle between our radial unit vector and our differential path vector is always going to be 90 degrees because we are on a circular arc. So that being the case, the sine of 90 degrees is just 1. So here is our simplified version of the Biot-Savart, and it is simplified to our specific geometry. Now we can continue. So we have two differential elements, our differential magnetic field element and our differential path element. So what are we going to do? We are going to integrate both sides. So let's go ahead and do that. So as we integrate the left-hand side, we just get the strength of the magnetic field. And that's all equal to the integral of permeability of free space times the current in our wire, circular arc, times 4 pi times our differential path element divided by the distance from the center of our circular arc to the wire squared. Notice that I do not have a closed loop integral like Ampere's law. That's going to be critical because we're only going a certain path, ds, from our start point, which is down here, to our final point up there. Alright, so this is a different path vector than Ampere's law. Alright, so let's actually evaluate this integral. Well, most of this stuff is just constant. So these 4 constants right here can go outside of our integral. Now we have to look at our overall total length of our circular arc. So is there an equation on the PRC that we can go to help us out? Of course there is. Okay, so go to your PRC, look at your kinematics section, and look at those link sections, or the link equations. It's a little box in between the translational and rotational portions. You should see in there a S is equal to theta r, or r theta. Either way, it represents the arc length and the radius of a circular arc. Okay, so we're connecting translational motion and rotational motion. That's that link equation. Well, that applies for us because here we have a differential path element and we can relate that right there. So let's keep going. So over the course of our integral, does our distance from the center of our circular arc to the outside of the wire change? Well, in this case, it doesn't. So we can move that 1 over r squared outside. So once we've moved that out, now we look at our differential, where our differential is no longer ds, it's now d theta r. Well, we have the full differential of 2 variables. What should we do with the differential of 2 full variables? Chain rule, anyone? So let's go ahead and do that on the side. So as we break this down, we have our second variable times the differential of our first, plus our first variable times the differential of the second. Well, as we said, our distance from the center of the circular arc to the wire isn't changing over time, or isn't changing at all. That's 0. So all we're left with is this r d theta element. And since r is a constant, we again pull that out. So we now have permeability free space times I, the current, over 4 pi r, since the one from our differential canceled with one of our radius variables in the denominator, times the integral of d theta, where theta is our angle of deflection of our circular arc. So the final result is, I'm going to do this kind of over here, the strength of the magnetic field is equal to mu naught times the current divided by 4 pi times the radius of our circular arc times our angle phi. And that is the total angular deflection of our circular arc. Okay? And that's because the integral of d theta is just theta, where our initial is 0 and our final is phi. And we can put that in our limits of integration here from 0 to phi. And that's how you derive the strength of the magnetic field for a circular arc. Now instead, again, we use the law of Biot-Savart instead of Ampere's law. Alright, so next up is our solenoid. So we're going to start with Ampere's law, and we're going to make the assumption that we have an ideal solenoid in that the magnetic field is only present inside the solenoid, and it is a uniform magnetic field inside. So I did as best as I could, but an ideal solenoid, the distance between these magnetic field lines would be the same, whether you are up here at the top, down here at the bottom, along the wall here, or in the center. It doesn't matter. We have a uniform and constant magnetic field inside the solenoid. Okay. Now, as far as applying Ampere's law to a solenoid, I'm going to choose my Amperian loop that is closed to go along the path A, to along B, along C, and along D, back to where I started. So first I'm going to look at part A, then I'll do B, C, and D. Now if you remember from Gauss's law, specifically we had a problem where we were looking at the enclosed charge inside of a cube, and we were looking at how the electric field interacted with our differential area vectors. Okay, instead of having area vectors, we have our differential path length vectors. So in this case, we have path length A, B, C, and D. So this is a vector, that's a vector, that's a vector, that's a vector. Alright, so we'll break down this closed loop vector. So we have, this is what we start with, but as we break it out into its four pieces, we have the magnetic field dotted with ds A plus the integral B dot ds B C and D. And that's still all equal to our permeability free space times the enclosed current. Okay, so now we get to look at our vectors. In the case of the first one, our vector ds sub A is pointing in this direction. So if we do a quick vector diagram, we have the magnetic field and we have ds sub A. The angle between our vectors is 90 degrees, and we can break out our dot product into magnitude and angle form. And the cosine of 90 degrees, 0. Okay, so that means that there is zero magnetic field traveling along that vector because they are perpendicular. As we look at B, because we assume that we have an ideal solenoid, the magnetic field outside is 0. So for this one, that 0 doesn't contribute. We look at C, we have a very similar situation to our path A, but our vector diagram's a little different, and it is same direction of the magnetic field, but our differential path length is pointed up. Still 90 degrees, so this still does not contribute. So we have 3 of our 4 legs do not contribute to our Ampere's law portion. What about the last one? Well, in this case, we have our magnetic field traveling in the same direction as our path length, or our differential path length. Better yet, we're inside the solenoid. So not only do we have a solution here, but we're inside the solenoid, so it's not just 0. So as we apply that, we have a uniform and constant magnetic field. So that is pulled out of the integral. And the angle between our vectors is zero degrees. So the cosine of 0 is 1. And we're left with that. Okay, so we have B and then some length D, we'll say from 0 to L, BL, and that is equal to mu naught I enclosed. And we're almost done. The question is, what is the enclosed current? It's not just the current in the wire, because look how much current I have enclosed by my loop. In this case, I have 1, 2, 3, 4, 5, 6 turns, each of them carrying the same current. So the enclosed current in this case for our Amperian loop that we have described is equal to 6 turns times the current in each wire, or each turn. And my length is some length d, but this is all going to come out in the wash here in a second. So the strength of the magnetic field is equal to mu naught, the permeability of free space, times the current, times the number of turns inside my loop, times the length of a portion of my loop inside my solenoid. And we can further describe our number of turns per length as a turn density. So mu naught times the current in each loop times n, the current density. Now that's not on your PRC, that's something that you will need to remember. Alright, so that's where this portion or this equation on the PRC comes from. Next up, the toroid. Alright, last up is our toroid. So we've taken our solenoid, we've wrapped the length around so that the length is now the circumference. The problem is that we need to look at the current density of the inside and the outside radius. So in this case, on the inside, the turns are much closer together than they are on the outside. Now I've counted the circles here to make sure that they are equal in number. So I connected a gray line to each of the circles to represent the wire circling around this inner portion. So our actual toroid is in here in the center where we see our clockwise direction of the magnetic field. So because we have different current densities or different turn densities on the inside than the outside, we will not have a uniform magnetic field on the inside. But that's okay. Ampere's law will take care of us. So as we move on, we need to look at first what is the direction of the magnetic field and what is going to be our Amperian loop. Now the Amperian loop I've chosen to take is there in purple. It is in the clockwise direction, and it really doesn't matter where I put it so long as it keeps the same distance r from the center of my donut, or center of the toroid. Okay, so as I go around my purple path, I'm keeping the same distance from the center of the toroid the entire time. And at that same distance, my magnetic field will be constant. Now if I were to change my radius, then I will have a different magnetic field. But along my Amperian loop path, it is constant. And if it's constant, then that means I can pull it out of the integral. And so as we put this into magnitude and angle form, the angle between our vectors is 0 degrees because they are both traveling in the same direction. And the cosine of 0 degrees is just 1. And now I can look at the closed loop integral of our differential path, which, as you add them all up, is just the circumference of a circle. And the circumference of the circle is just 2 pi times the radius. Now the radius is the distance from the center of my toroid to my path element. That's also going to be the same point in which I'm measuring the strength of the magnetic field. And that again is still equal to the permeability of free space times the current enclosed. And that enclosed piece is going to come into play here in a second. Alright, so I have the strength of my magnetic field is equal to permeability of free space times the current enclosed divided by 2 pi r, the circumference of my Amperian loop. Now, the current enclosed only looks at the current in my loop. Well, how much current do I have in my loop? That depends on how many loops I have. Here I have 1, 2, 3, 4, 5, 6, 7, 8, 9 loops. So each of those loops is carrying the same current. So I can say that I have one more. It is the number of loops times the current in each loop divided by 2 pi r. Now as we put this into the form that's on our PRC, we have the strength of the magnetic field is equal to the permeability of free space times the current times the number of turns in our toroid divided by 2 pi times the distance from the center of the toroid that we are measuring the magnetic field. And there is our equation from the PRC derived from Ampere's law. Now this covers all of the geometries that we'll be using in this course: the straight wire, the circular arc, the solenoid, and lastly the toroid. You've seen them derived from two different types of methods, either using the Biot-Savart law or Ampere's law. Either one we're dealing with differentials and the other we're dealing with integrals. Alright, so that covers this portion of, it's more of a reference video, a theoretical reference video for how the equations on the PRC are derived. Alright, thanks a lot.